Hello friends, now we shall study a counting principle. First we define this product set HK. If H and K are two subgroups of G, we define H into K is equal to X belongs to G, those elements of G such that X is equal to HK. H belongs to H, K belongs to K. That means every element in HK is of this form, H into K. This notation, we denote the element of capital H as small h and small k belongs to capital K. So this is the set H into K is defined. Every element is in the product form. First element belongs to the first set, second element belongs to the second set. Now when this HK will be subgroup of G, H and K are given as subgroups, whether the product is subgroup or not, that is stated in the lemma 8. HK is subgroup of G if and only if HK is equal to KH. That is commutative. This product of sets is commutative, and then this becomes subgroup. And there are two parts. Assuming first we shall consider HK is equal to KH, then we prove HK is subgroup of G. So first suppose that HK is equal to KH. So therefore for H belongs to capital H, K belongs to capital K, we have HK. This is an element in HK, and this set is equal to KH, therefore this must be equal to product of element in K and element in H. So we will consider this as K1H1. For some K1 belongs to K, H1 belongs to H. This is what we have written, HK is equal to KH. Element in HK is equal to element in KH, because set equality implies every element in HK is in KH and conversely. Now to prove this HK is subgroup, we have to prove HK is subgroup of G. So we have to verify that HK is closed and every element has inverse in HK. So this is the criteria for subgroup. When a set is said to be subgroup, it is closed and inverse exists. So HK is closed and every element of HK has its inverse in HK. Then HK will be subgroup. These two are necessary conditions for subgroup. First we shall consider HK is closed, and for that purpose let X belongs to, or X is in the form HK, belongs to HK, and Y we write H dash K dash, this belongs to HK. Elements in this set are written in product form. So by definition, here we have defined every element of HK is in the form HK, and thus we have taken two elements. Therefore the product XY will be HK into H dash K dash. Now we shall consider the middle two elements, KH dash. Now, and for since KH is equal to HK, therefore this element KH dash can be written. This is an element in KH is equal to H2 K2, element in HK. We are using different notation for different elements. Here we have used notation HK, H dash K dash, H1 K1, K1 H1, etc. So we use suffix 2 now. KH dash, element in this is KH dash. We have considered this element particularly. KH dash must be equal to element of this form hk, h2 k2. For some h2 belongs to h, k2 belongs to k, and thus therefore this xy becomes, therefore xy is equal to, or this may be written as h kh dash into k dash by associative law. The middle two elements are grouped, and now this is x into y means this element h, and you see kh dash is h2 k2 into k dash. But again we use the associative property, and this can be written as hh2 into k2 k dash. And now observe, this element h into h2 belongs to capital H, because both h and h2 belongs to h, and the product also belongs to h. So this is an element in h, and this is an element in capital K. So therefore this belongs to h into k, element in the product form, and thus this proves the closure property. Hence, or thus, hk is closed. Now next we shall consider, we have two inverse also exist. Two properties are to be proved for subgroup, closure and existence of inverse. What is x inverse? X inverse, x we have considered hk, inverse of hk, and inverse of hk is by reversal law, k inverse h inverse. So this we have proved earlier. A b inverse of ab is equal to b inverse a inverse, reverse, order is changed. First we have to write b inverse, then a inverse. That means ab and b inverse a inverse are inverses of each other. Therefore this law, reversal law, holds, and thus this is k inverse h inverse, and this element belongs to which set? Capital K first and capital H. This belongs to kh, but kh is the same as hk, and therefore we can write this is equal to h. And finally what we have, x inverse belongs to hk, and thus inverse exists in hk. Therefore every element has inverse in hk, has its inverse. Inverse in hk, and hence, so this we have proved. Hence hk is subgroup. hk is a subgroup of G. So this proves first part of the proof. Assuming hk is equal to kh, we have proved hk is subgroup of G. Now the converse part, or second part, we shall assume hk is subgroup of G, and then we shall prove hk is equal to kh. So secondly, we shall consider, suppose now hk is a subgroup of G. Now let h belongs to h, k belongs to k. So then this implies hk belongs to hk by definition, and its inverse also belongs to hk. So this implies inverse of hk belongs to hk. But what is the inverse of hk by reversal law? Again, here we have k inverse h inverse. So this implies k inverse h inverse belongs to hk. But you see, k inverse h inverse is an element in kh, and element in kh is in hk. So therefore kh is subset of hk. To prove here, assuming this, what we have proved, hk is equal to kh. So this we have to prove. We shall mention here, we have to prove hk is equal to kh. So this we have to prove. And for proving hk is equal to kh, we shall prove that hk is subset of kh, and secondly kh is subset of hk. If the two sets are subset of each other, they are equal. So this is an element in KH and it is in HK. So KH is subset of HK. So thus KH is subset of HK since K inverse H inverse belongs to KH. Element in KH is in HK. Next, let X belongs to HK. We have to prove HK is subset of KH, and for that purpose we have considered X belongs to HK. So therefore X inverse also belongs to HK, and that we will write in the form HK. X inverse is an element in HK. Inverse exists in HK. Every element has its inverse in HK. So X has its inverse in HK, means X inverse is in the form HK. So this belongs to HK. And now we shall consider X. Or therefore X is equal to double inverse of X. Inverse of X inverse. This property also we have proved. And that is, what is X inverse is HK. And its inverse. And its inverse is K inverse H inverse. So therefore this is K inverse H inverse. And this belongs to KH. Element of K, element of H. So this belongs to KH. So thus X belongs to HK implies X belongs to KH. And therefore X belongs to HK implies X belongs to KH. And thus HK is subset of KH. And from this, or you see these two results from 1 and 2, or this is, or you may consider 1 and this as 2. Hence from 1 and 2 we have HK is equal to KH. Equality holds. And this completes the proof of the lemma. So if H and K are abelian groups, subgroups, then HK is always a subgroup of G. Because if the two groups are abelian, then HK is equal to KH always holds. When this result need to prove where it is not given that they are abelian. So if the two subgroups H and K are abelian, then this always holds and HK becomes always a subgroup of G. Now we shall consider the next result as theorem second, and this is actually the counting principle. If H and K are finite subgroups, G of orders order H and order K respectively. We denote order by this notation, order of O of H respectively. Then we want to express the number of elements, order of HK. Then order of HK is equal to order of H into order of K divided by order of H intersection K. So this is actually the counting principle. How to count? Order means number of elements in the set. Order of H means number of elements in H. Order of K, number of elements in K. Now we want to count the number of elements in HK. HK we have defined earlier, and this is equal to order of H into order of K divided by order of H intersection K. Now to understand the meaning of the theorem, we may consider an example. And the example we shall consider is, say let H be the set 1 minus 1, or it is a subgroup under multiplication. G is the subgroup 1 minus 1 I minus I. We have studied this these examples earlier. These both H and G forms a group, and these two together can be considered as subgroup of C, complex number, subgroup of complex numbers we shall consider. And then so we want to verify this theorem. So H and K are given. What we have to write is H intersection K and HK. Then what will be HK? HK, or see, this is to be considered as K. HK. And HK will be the product. We will see the product 1 into 1. Multiply by 1, pre-multiply by 1 to 4 elements, 1 into minus 1. 1 into I, and then 1 into minus I. Then further minus 1 into 1, minus 1 into minus 1, and minus 1 into I. This is usual multiplication. Minus 1 into I and minus 1 into minus I. So these are the elements in HK. But you see whether these are, how many elements are there? Apparently we see these are 8 elements, but these are not different, and we should not count the repetition. So here this is the element 1, this is minus 1, this is I, and this is minus I. Again this is minus 1, so that means these two are the same. This is 1, so these two are the same, and minus I is same as this, and last is I. So therefore only elements, distinct elements are 1, minus 1, I, and minus I. Actually this is the same as K. So HK is this element, or this set. Now what is, we are writing the sets. HK we have written. What is H intersection K? Intersection of two sets, H and K. Obviously it is 1 and minus 1, common elements. So 1, minus 1. Now we shall write the orders of each. So what is order of HK? Number of elements in this. Or we may first write order of H. Now order of H is 2. Number of elements in H. Order of K. Order of K is number of elements in K, 4. And order of H intersection K. Order of H intersection K, number of elements in H intersection K are 2. So thus, and next we shall write order of HK. What is order of HK? Number of elements in HK. You may see these are also 4. And thus whether the theorem is verified or not. So we shall see order of HK. Order of H into K, this is equal to order of H. Order of H into order of K divided by order of H intersection K. So that means 4 is equal to 2 into 4 divided by 2. And thus this is verified. So the theorem is verified. So this is the meaning of this theorem. So the product may have some duplicate elements or repeated elements, and that repeated elements we have to delete, and we have to consider only the distinct elements in the set, and that counts the order of the set. So to prove, we shall consider here first two cases we have to consider. When order of H intersection K is 1, then these two are equal. That is, order of HK is equal to order of H into order of K. We will consider the proof. First we shall consider the case in which this H intersection K is E, trivial. That is, H is subgroup, H is subgroup, K is subgroup. A subgroup always contains identity, and therefore their intersection will not be empty. It must contain the identity element. And if it contains only identity element and none other, then what will be order of H intersection K? Therefore, order of H intersection K will be only 1. And in this case, the result becomes, so order of HK is equal to order of H into order of K. So in this case, the result is order of H intersection K is equal to order of H into order of K. And we shall suppose this as our result 1. Now we have the by definition of HK. We have HK is equal to the element H into K, such that H belongs to H, K belongs to K. Every element of HK is of the form. So this is HK is equal to the set HK, H belongs to H, K belongs to K. In that way only we have formed this, or earlier we have defined this. Now when this HK, when this result will not hold, if there is, now this result does not hold here because the intersection contains two elements. Now if you consider order of HK, it is 4, order of H is 2, order of 4, K is 4. So here order of HK is not equal to only order of H into order of K. That is 8, 2 into 4, 8, and this is 4. We have to divide it by order of H intersection K. Here this is general case, and in this case only the intersection contains only one element. This is the case we have considered particular case, and here we have considered general case. Here H intersection K is not only equal to identity, it contains two elements, and therefore we have to divide it by 2. So repetition occurs in such case whenever the intersection contains more than identity element. Now here there is no repetition, we have to say, and the result, this result will fail only if there is a repetition in the elements of HK. So here it is not intersection but HK. The result is order HK, and this is 1. So order of H into order of K, and we have by definition this as HK. So the result 1 will fail. So the result 1 will fail or will be false. Only if HK is repeated at least twice. Repeated, or that we may say duplicated, at least twice. Two times. Or the element is repeated, then this will not be true. And if it is not repeated, then this will be true. So that is for some, when this is not true, for some H not equal to H1 belongs to H. So we have HK is equal to H1 K1. This is duplication. Element HK is duplicated. Or in the earlier example, what is the duplication of element? Say we have 1 into I is same as minus 1 into minus I. So this is duplication. This is HK and this is H1 K1. And if this happens, then the element is repeated, otherwise not. And from this we shall pre-multiply. Pre-multiplying by H1 inverse and post-multiply by K1 inverse, we get. Now what is the meaning? Shifting the elements. Pre-multiply by h1 inverse means h1 inverse is to be transferred on this side. And post multiplied by k1 inverse means this k1 inverse is to be transferred on other side. So what we shall get is, if you pre-multiply by h1 inverse, then we will have and post multiplying by k inverse we shall consider inverse of. So that means this h1 we are shifting on this side, and this k we are shifting on this side, and thus we shall get, or we may perform these steps separately and we will get like this. So h1 inverse will appear here into h is equal to h1 inverse into h. If the element is shifted on other side, it becomes its inverse. So h1 inverse into h, and right side is k1. So shifting these elements on either side, we get h inverse, h1 inverse h is equal to k1 into k inverse. Now h1 inverse h belongs to h, k1 into k inverse belongs to k. These are the elements h, small h are elements in h, small k are elements in k, and therefore we have this belongs to capital H, this belongs to k. Therefore h1 inverse h belongs to h intersection k, because these two are equal. So h1 inverse h is equal to this, means this element is equal to h1 inverse h, and that belongs to h. And thus, but h intersection k is E. We are considering this case, h intersection k is E. Both these elements are equal, and therefore this element belongs to the intersection of two sets, and which is E. And thus this implies h1 inverse h is equal to E. Now we pre-multiply by h1 on both sides. So what this implies is h is equal to, if you pre-multiply or if we shift this h1 inverse on that side, it becomes h1 into E. H is equal to h1e, and that is h1. So thus we get h is equal to h1, but this is a contradiction. Why? We have assumed here there is no duplication of the elements. H is not equal to h1, that we have considered. The result is false only if the element hk is repeated at least twice, and we have assumed for some h not equal to h1. This is our assumption, and we get here h is equal to h1. So this is a contradiction. Since our assumption is h not equal to h1, and thus no element in hk is repeated. Here we have assumed here, if it is repeated, then h not equal to h1. In that case, this repetition happens. Hk is equal to h1 k1. Therefore, no element in hk is repeated or duplicated. And thus we get the result. Therefore, we have order of hk is equal to order h into order k. Now we consider the general case where h intersection k is not equal to E. The general case of h intersection k not equal to E. And here we shall prove that an element in hk occurs exactly order of h intersection k times. So we shall prove that an element in HK occurs or is repeated, or we may say it is duplicated, repeated or duplicated exactly in order of H intersection K times. Repeated elements occur in order of H intersection K times, and that's why if you prove this, then we divide by order of H intersection K, means we divide by the repeated number of elements and we get exact distinct elements. So this we shall prove, and for that purpose we consider let H1 belongs to H intersection K. Then we can write HK as H1 inverse K, and we may group this. Now you see, we write HK H1 inverse K. H1 and H1 inverse gives identity, and therefore H into identity into K is H2, and we suppose this as 2. Now H1 belongs to capital H, since the reason for this is H belongs to H. H1 belongs to H1, actually we have supposed in H intersection K. So H1 belongs to H intersection K, but this is subset of H. Intersection is subset of both the sets. H intersection K is subset of H, H intersection K is subset of K also. And thus H belongs to H, H1 belongs to H, means H1 belongs to H. Similarly, H1 inverse K, this belongs to K. And reason for this is, since H1 inverse belongs to H intersection K. How? Because H1 belongs to H intersection K, therefore the intersection of this is a subgroup, and its inverse also is in H intersection K, and H intersection K is subset of K. So this set is a subset of H, we should note. And this H1 inverse belongs to K, and K belongs to K. Small k belongs to K, and therefore H1 inverse K belongs to K, and thus this HK is repeated at least order of H intersection K. Now H1 is an element in H intersection K, and therefore we have a written HK as H into H1 inverse into K. Similarly, if H2 is an element in HK, then that HK can also be written in terms of H2. See how this follows will be HK will be equal to H2 inverse K, and therefore this can be written in terms of H2, and thus we can write HK in terms of H2. So therefore this is the element which can be written in terms of H1, H2, etc. So how many times an element in HK is repeated, that we are considering. If H1 is in the intersection, then HK is written in terms of H1 and its inverse. And if H2 is in, again, intersection of H and K, then we can write HK in terms of H2 and its inverse as H2 inverse K. And thus this can be continued. If H3 is the element in H intersection K, then HK can also be written in terms of H3 inverse K. And therefore HK is repeated at least order of H intersection K times. So therefore HK is repeated. So So this element belongs to HK is repeated at least order of H intersection K times. As many elements are there in H intersection K, that times this HK can be repeated. But all the repetitions are exactly this number of times. That also we have to consider. Also, we have to show. Also, if HK is equal to H dash K dash, then, or we may consider instead of H dash K dash H1 K1. If HK is equal to H1 K1, then as in the earlier case, we can consider here we post multiply by K1 inverse and we pre multiply by H inverse. So this can be, that means we transfer this H on this side and we transfer this K on this side, and then K into K1 inverse is equal to H inverse into H1. This we can write, and suppose this is equal to U. Therefore, U belongs to H, U belongs to K, means U belongs to H intersection K. And further, we can write from this H1 is equal to H1, we pre-multiply both sides by H, and this H inverse is transferred on this side, it becomes H. So H1 is equal to H into U. And similarly here from this K1 inverse, we take first and this last. So K1 inverse can pre-multiply by K inverse. K1 inverse will be equal to K inverse into U. And from this K1 is equal to, take the inverse on both sides, and inverse of this K1 is K inverse U, its inverse, and that is reversal law. Inverse of U into double inverse of K is K. So U inverse into K. This is K1. Now we can consider again HK. So HK can now be written as HK is equal to, in terms of U we will write HU like this. H1 inverse K. Instead of H1 we consider now U, because here U belongs to H intersection K and here H1 belongs to H intersection K. This HK is written in terms of H1 and its inverse. Now this HK we shall write in terms of U and inverse of U into K. Same like this in second. And but what is HU? HU is H1. So this is equal to H1. And what is U inverse K, or we may group this. And what is U inverse into K? That is K1. So therefore this is K1. And that means this HK is equal to H1 K1 is written in terms of U. So therefore all duplicated elements are written in this same form, and that means duplicate elements occurs exactly as the number of elements in H intersection K. So this shows that all duplications of elements HK occur exactly in according to second. And that means duplicate elements occur exactly in order of H intersection K. That is exactly in order of H intersection K. and thus distinct elements. So duplicate elements occur order of H intersection K times, and therefore the distinct elements can be obtained by dividing this number of duplicate elements, or that means order of H intersection K, and we have to divide order of H into order of K by order of H intersection K. So therefore the distinct elements, number of distinct elements, we shall say the number of distinct elements in HK are given by order of HK is equal to order of H into order of K divided by order of H intersection K, and this proves the theorem. Counting principle. This completes the proof. So here we have considered two cases. In first case, the H intersection K is only one element, single element identity. In that case, the result is order of HK is equal to order of H into order of K. And in the second case, if it is this is not only the identity, it may contain more than one element, then duplicate, how many times the duplicate elements occur, that we have to consider, and then we have to divide out by the duplicate number of elements. For example, we have considered H as 1 minus 1 and K as this 1 minus 1, I minus I. Then this element 1 into I is same as minus 1 into minus I. So this is duplicate element. I is equal to I, but it is written in two ways, and therefore such duplications occur here in two number of ways, because the intersection of H and K is 2. So these elements are repeated, and therefore we have divided in the example earlier considered as order of H is 2, order of K is, say, also order of K is 4, and order of H intersection K here is 2. These are the intersection elements in the intersection, and thus we get order of HK, which was 4, as 2 into 4 divided by 2, and the theorem we have verified. So the same thing is written here. Number of duplicate elements occurs exactly in order of H intersection K times, and this completes the proof. So next time we shall consider problems on subgroups. Thank you.